Hello everyone, I'm Maxime Trebitsch. I'm a postdoctoral fellow at MPA and at the University of Heidelberg. And first of all, let me thank the organizers for setting up a conference like this, and in particular for organizing these recorded talks. Today I'm going to present the results from the Obelisk simulation, which is a collaborative project I've been leading with Johan Dubois and Marta Volonteri in Paris, and whose main goal is to study the contribution of galaxies and AGNs to reionization. I'm not going to go over the process of reionization because this is already the main goal of this conference, but what I'm mostly interested in here is understanding what are the sources of reionization. So which are the first stars, first galaxies, and first black holes that produce the bulk of the ionizing photons that reionize the universe in 1 gigayear or so. Usually when people talk about sources of reionization, there are mainly two different types of sources, either AGNs or galaxies. And usually AGN are discarded from being the main sources of reionization because counting quasars at high redshift indicate that there are enough of them to keep the universe reionized at redshift 4 and above. So basically we need another source of radiation, and a very good source are galaxies, in particular faint galaxies. If you integrate the UV luminosity function down to magnitude of -13 or so, you get, provided you assume some escape fraction that's reasonably high, you get that roughly, it takes roughly 1 gigayear for most of the hydrogen to be reionized in the universe. So this is a nice story and it seems to work, but in the recent years, there have been more and more studies suggesting that the contribution of faint AGNs have been underestimated. In particular, counting the very faint AGNs at redshift 4, 5, and 6, it seems to indicate that they could contribute up to 30% to the UV background. Of course, there are some assumptions that go there. In particular, this assumes that all these faint AGNs have very high escape fraction, and that the contribution from the galaxy is negligible to the UV light that you see. So I'm not an observer, so I cannot directly weigh in on these problems, or these assumptions at least, but what I can do is to turn to my favorite tool, which are simulations. And to study reionization, there are mainly two types of simulation. One is to do very large-scale simulation, like the CODA2 simulation on the left here. And another one is to study the details of the physics during the epoch of reionization, in particular, studying the formation of galaxies with incredibly high resolution, like showcased here by the Sphinx simulation. Unfortunately, if you want to study the contribution of AGNs to reionization, you have to bridge both worlds, basically, because you need to study the processes inside the galaxies that are responsible for the growth of the black hole and the production of ionizing photon, etc. But at the same time, you need a large enough volume in principle to capture enough AGNs to have some statistical significance. And this is computationally undoable at the moment. And so the only approach that allows us to study AGN contribution to reionization so far is to select a very specific environment that will be favorable to black hole growth. And this is what we have done with the Obelisk project. So the Obelisk project is a zoom simulation on not just one galaxy, but a whole environment. And in particular, we focused on a protocluster region. The simulation is aimed to go down to redshift 2. It's currently at redshift 3.5 or 3.4 now. And the main feature of the simulation are the following. So this is a high-resolution galaxy formation simulation, where we do follow the gas, the dark matter, and the radiation. And this is a high enough resolution to start to study the inside of galaxies. We do include supernova feedback, star formation, black hole growth, black hole feedback, etc. But more importantly, we're tracking separately the sources of radiation that are stars and AGN. So we track the radiation coming from both, and this way we can assess their contribution to reionization. When I say this is a high resolution simulation, the idea is that we don't just have a zoom on one galaxy, we have a full environment as showcased here on the top left, but at the same time, the resolution is high enough that we can resolve the inside of galaxies. And this is, for instance, a spiral galaxy at redshift 3.7 or so. Now I'm going to show a quick movie illustrating the evolution of the region, the protocluster region, and the collapse of the structure. And we see now the ionized gas. We see ionized bubbles that are growing under the effect of radiation produced by stars and AGN in the simulation. Yeah. Now we will see the gas temperature, and we do see traces of filaments. We see that most of the gas at that time is completely ionized, around 10 to the 4K or so, but we still see very hot bubbles that are caused by virial shocks and agent feedback. Now I'm just showing the skeleton in gas density, where we see that we have these large-scale filaments that are connected, and at the center of these we have some massive galaxies, but we also have other galaxies everywhere, and now we see the stars. And again, we see these massive galaxies here, there, and there, for instance. And all over the place, we do have a large sample of smaller galaxies as well. So this means that we can really use this kind of simulation to study both galaxy formation, but more importantly, the contribution of all kinds of galaxies to reionization. In terms of galaxy population in this simulation, what do we have? Well, we should not expect this to be comparable to the average of the universe, because as I mentioned earlier, this is a protocluster region. So this is a region that will be much more actively forming stars than the field. And indeed, if you compare this blue and purple curve to the observations of Pascal Hoesch and collaborators, we do see that at all redshifts, there is a factor of 10, at least, more stars formed in the Obelisk simulation. But the good news is, when you actually compare apple to apple, in particular protocluster to protoclusters, you do see that the Obelisk simulation falls in line with the high-redshift protoclusters that have been detected so far. Now, moving on to a specific redshift, looking at redshift 6, for instance, we can look at the UV luminosity function. And in black here, I'm showing the raw UV luminosity function extracted from the simulation. And the data points are compilations from different UV luminosity function. And I'm showing, in particular, the points from Akimatek and collaborators with these blue dots. And again, we see that there is a strong overestimate in the simulation compared to the UV luminosity function. But again, this is not completely unexpected. One reason is that we have a protocluster, but the second reason is that we have dust in these galaxies. And in particular, in the massive galaxies, at the bright end, we do have a lot of dust. And when we take that into account, we get this red shaded area where we see that the bright galaxies are completely disappearing, and we get something that's way more comparable with observation. It's still above the average luminosity function that we get from Atek et al., for instance, and this is just because this is a protocluster. If we compare the Obelisk luminosity function to that found in the BDF field by Castellano et al. In 2016, we do start to see that there is a much better agreement. In terms of black hole population, we can do the same kind of story. I'm not going to go in the details, but effectively, we do see that black holes are growing happily in the Obelisk simulation, especially in massive galaxies. We do see that the black hole mass to stellar mass relation falls well in line with the constraint at redshift 0 for the scaling relations. There is a second blob here that is mainly low mass galaxies. And in these low mass galaxies, we do not expect the black holes to grow. And so what we see here is just the seed black holes that are not growing until the galaxy is massive enough, and then they are growing. So overall, that means that we have a reasonable galaxy and black hole population, and we can use this simulation for reionization because we have reasonable sources. What I'm showing here is just a poster of the various stages of reionization. We do see that the very first stage, sorry, of reionization corresponds to very high redshift, redshift 11 or so, when we see that the first massive galaxy are reionizing their environment, and then it takes 500 megayears or so for all of the universe to be reionized. And by redshift 6 or so, most of the gas in the high resolution region in the simulation is reionized. More quantitatively, we can compare the result of the Obelisk simulation in blue here to various observational probes shown as data points here, and with the Planck constraints shown in purple shaded area here. And what we see, and it's kind of surprising, is that in the Obelisk simulation at least, the timing of reionization is roughly consistent with that of the average universe. And the reason I'm saying this is surprising is because we have many more sources, as I just showed. So we could expect earlier reionization for this protocluster region. But at the same time, we also have more gas in this region, so we could expect later reionization. And what we find in the end is that there is these two effects are balancing each other, and the reionization history in protoclusters seems to be consistent with the average reionization history of the universe. So now, going back to the sources of reionization, I mentioned when I presented the simulation that the Obelisk simulation traces separately the sources of radiation that are stars and AGN. And so we can count how much radiation is produced by these two types of sources and how much is escaping in the intergalactic medium. And if we focus on the thick lines here, we see in blue the total amount of radiation escaping from galaxies. In orange, the total amount, the galaxy contribution to this total, and the thick green line is the contribution of AGN to the total ionizing emissivity. And what we see is that during all the epoch of reionization, highlighted in orange here, the ionizing emissivity is largely dominated by stellar population. And it's only at the very end of the simulation, around redshift 4 or so, that AGN start to take over. Interestingly, what we can do is compare how much radiation is produced to how much is escaping. And if you take the ratio of these two quantities, that gives you the escape fraction. And we can do that population by population. And that's what I've done here. So the orange line is the average stellar escape fraction, while the green line is the average escape fraction from AGN. And what we see is that even if AGNs have a much higher escape fraction than galaxies, by a factor of almost 10 during the epoch of reionization, they still contribute much less to the total UV background. Finally, quantifying the total UV background in the Obelisk simulation, we can compare the photoionization rate to observations. And again, I'm using the same color coding. So the blue line is the total photoionization rate from galaxies and black holes. The orange is the contribution from galaxies. And this thick dotted green line is the contribution of AGNs. And what we see is, again, that at least where we have constraints, the Obelisk simulation seems well in line with observational constraints. But more importantly, we do see that during the whole epoch of reionization, again, it's mostly galaxies that are contributing radiation to the UV background. In particular, if you look at the AGN contribution, it seems to be very well compatible with both observations and models of Kull-Carnier-Tam, for instance. So this leads me to my conclusion. Very quickly summarizing, the Obelisk simulation is a simulation that models the assembly of a protocluster during the first 2 gigayears of the universe, so during reionization, but also after. We follow a large population of galaxies and black holes with very high resolution of 30 parsec or so. And what we find is that in overdense regions, reionization is mainly driven by star-forming galaxies, even though these regions are very favorable to black hole growth and AGN activity. Finally, at the very late, very end of reionization, and even below that, we see that at redshift below 5, AGN starts to contribute significantly to the UV background. Thank you very much.